one-dimensional two-noded cubic beam element matrix is a single two-noded cube beam element has two nodes with 2 degrees of freedom at each node, one vertical displacement and one rotation or slope. There is a total of 4 degrees of freedom and the displacement polynomial functions assumed should be 4 terms. So we have to choose cubic polynomial for vertical deflections. Slope is the derivative of the vertical deflections. The vertical displacement is equal to v plus bx plus ax square plus dx cube. The slope dy by dx is equal to p plus 2c x plus dx square. Apply the boundary conditions. X is equal to 0, v is equal to v1, is equal to a what a is equal to v1, x is equal to 0 and v is equal to v1. At x is equal to L, so v is equal to v3, so v2 is equal to a plus bl plus cl square plus dl cube. At x is equal to L is equal to b plus 2cl plus 3dl square. So v is equal to n1 v1 plus n2 v2 plus n3 v3. So n3 v4 where so n1 is shape functions 1 minus 3x square by l square plus 2x cube by l cube. So n2 is equal to x minus 2 x square by l plus x square by l square. So n3 is equal to 3x square by l square minus 2x cube by l cube. So n4 is equal to x square by l plus x square by x cube by l square. So development of element equations here. So this is the equation given here. So finally the stiffness matrix is equal to Ki. 12 L cube 6 by L square minus L is 12 by L cube 6 by L square 6 by L square 4 by L minus 6 by L square 2 by L minus 12 by L cube minus 6 by L square 12 by L cube minus 6 by L square plus 6 by L square 2 by L minus 6 square by L cube, so 4 by L. So these are the things here. Then beam element. A beam is a long slender structured member generally subjected to transverse loading that produces significant bending effects as opposed to twisting or axial effects. An elemental length for long beam subjected to arbitrary loading is considered for analysis. For this element beam length L, we assign 2 points of interest, that is ends of beam, which become the nodes of the beam element. Bending deformations is measured as a transverse, that is vertical displacement and a rotation slope. Hence for each node we have a vertical displacement and a rotation, that is slope, 2 degrees of freedom at each node. For single 2-noded beam element we have a total of 4 degrees of freedom. The associated forces are shear force and bending moment at each node. The definite term K indicates the force or moment force required at 1 to produce a unit deflection or rotation, while all other degrees of freedom are kept 0. Upward forces are positive and upward displacements are positive. Counterclockwise movements are positive and counterclockwise rotations are positive. So formula required: cantilever being subjected to concentrated load at moments. So PL square by 2EI, PL cube by 3EI. So values so ML by EA depend upon the moment previous one based on the loads. So ML by EA is equal to ML square by 2EI. The element matrix and vectors. The derivation of the first column of stiffness matrix V1 is equal to 1 V2 and that's equal to 0, that is allow the first degrees of freedom to occur and arrest all other degrees of freedom. The deformed configuration is shown in figure. So initially you have a horizontal beam element. Since V2 is equal to 0, we can fix node J to produce an upward deflection at node I, that is allowing the first degrees of freedom to occur. Apply an upward force. First stiffness indicates the force or moment degrees of freedom, and the second stiffness indicates the displacement or rotational degrees of freedom, that is upwards. Table displacement degrees of freedom number and degrees of freedom number. Now the beam calculation is given by the figure shown here. We can others observe from the figure that the slope at node I is not 0. To make the slope at I equal to 0, we need to apply a counterclockwise moment. From referring the figure number 2, this moment will produce a downward deflection. So L square by 2E at node I of figures. In order to have a resultant, we need upward displacement at node. Upward displacement produced by force must be greater than downward displacement produced by the moment. So KL cube by 3I minus KL square by 2I is equal to 1. At the same time, the negative slope produced a node I by the force K, that it must be cancelled by positive slope produced by the moment K20. Now the force K11 must be cancelled by positive slope produced by the moment. So solving two equations fixed, and the reaction force and the reaction moment are assumed to be acting upwards and counterclockwise respectively. Now use force equilibrium equations to find fixed and existence reactions forces and moment equilibrium equation about node I to find out the end reaction moment.